All right, so we're back, and now we're going to talk about sort of the opposite of what we had been talking about with random assignment. What are some non-random methods for producing two groups? The best thing you can do, the most powerful thing you can do, is to do a repeated measures design. If it's feasible, given what you're studying, a repeated measures method is really awesome. What you do is you test the same people in both conditions. So in a two-group design, there are two levels on the independent variable. We still have that part. And now instead of randomly assigning some people to get one version of the independent variable and some people to get the other, instead you have everybody in the sample experiencing both conditions. This is really nice because it gets rid of any extraneous variables, anything that might be co-varying with the sex of the participants or the age of the participants. Like, none of that matters now. Because these are the same participants in both conditions. So honestly, if it's possible to do a repeated measures design, it makes a lot of sense to do it whenever you can. It doesn't work in all circumstances, but if it does, it's a good idea to use it. Basically, what you've got is the participants serving as their own controls. So each person provides the experimental data and the control data. And so we make our comparisons within each individual in their control and their experimental experience. You may learn in your next level training, either stats or research methods that's more advanced, you might learn that this is called within subjects, because in statistical terms, it's called within subjects. In design terminology, it's called repeated measures, same exact thing. So what's involved in this kind of design? So you have one group who, let's say with the Jelly Belly design, they experience the cherry one and they experience the Tabasco one. And for each of those, they produce a rating of the flavor expectation for each of those Jelly Bellies. Would this work? Could you give a person, let's say, the Tabasco flavored Jelly Belly first, have them rate their flavor expectation, and then give them the cherry flavored Jelly Belly and have them give their flavor expectation? Would it work? It might, but it might not. Now, once you've tasted the Tabasco flavored one, isn't that going to somehow bias or taint you for the kind of expectation you would have for the cherry flavored one? You don't get to see them simultaneously, right? I give you the Tabasco one, you examine it, you eat it, you rate it. Then I give you the cherry flavored one, you examine it, you eat it, you rate it. So you don't have them side by side, and so you can't look and see what the differences might be. If you could have them side by side, that might even be worse. I don't know. Because your expectation might not be based on strictly how it looks or something like that. It's being based on comparisons that aren't maybe part of my design. It's hard to do this one within subjects. Taste tests are hard to do within subjects. We typically do taste tests between subjects because once you've tasted one of them, you sort of have an expectation for the other one. You're already what we like to call tainted. You have experience. So probably that wouldn't work. Let me talk about repeated measures for another second. Let's talk about some examples where it would work. I conducted a study a few years ago with my son. He came up with the idea. He was in high school and he wanted to get a better graphics card for his computer so that he could have 120 frames per second while he played video games on his PC. And I was making the argument as a person who has some expertise in perception that it doesn't matter if you do 120 frames per second, your brain can't perceive that. And he was making the case that yes, it can. And he showed me a video of some guy doing it, and he did a within subjects test of himself, where he had somebody else decide what the frame rate was going to be on each trial, and then he would turn and look at the screen and he would say whether he thought it was 60 frames per second or he thought it was 120 frames per second. And he was able to recognize accurately, 60 versus 120 frames. But he said, well, I have a lot of experience playing PC games, and I've played with 120 frames per second. Let's get someone who doesn't know. And so he got one person and he had them do the exact same procedure, but that person had never played PC games. And so that person was at the chance level of guessing the frame rate. So we actually made an experiment out of that. That's what I just described is called an N of 1 study. So we decided to do an actual experiment. And so we recruited people who were either PC gamers or console gamers. Consoles only play at like 30 frames per second. There are a couple of opportunities where you might get as fast as 60 frames per second, but mostly not. And so we recruited people with different kinds of experiences, and then we had them look at multiple scenes from the video game Portals, if you know that one. And so we had multiple ratings per participant. They saw, I think, a total of 10 scenes, and each of them twice, because they saw it once in 120 frames per second and once in 60 frames, and they were all mixed up and in random order. But they saw a total of 20 across the two different speeds, and so each person served as their own control. They saw half of them at 60 frames per second, half of them at 120, and we wanted to see, are they accurately recognizing it? And it turned out the PC gamers could. We actually had that between subject component where it was PCers versus consolers, and then within subject component where it was across the different frame, the different scenes that we showed. And what was really interesting is it turned out the different scenes mattered. Some of the scenes were easier to tell than other scenes. And so, like very consistently, some of them people very accurately were able to recognize. Others, they were at chance level. So, but what that gives you when you have that repeated measures is you get rid of issues like maybe some people can see better. Maybe some people have better depth perception. Maybe some people, when they say they have experience playing PC gaming, meant that they have a lot. And some people meant, yeah, I've done it. And so we've got these individual differences of level of experience with it or something. All of that stuff was sort of controlled by letting each person be their own control. And so that's a really nice aspect of repeated measures. Like I said, as much as you can ever, if you ever design a study, if you can include components where the same person's tested more than once, that's a great idea. All right, what about another non-random assignment method, which is a matched pair design? So sometimes we want to make sure that certain characteristics get evenly distributed between both groups. We're going to usually look for things that we think might be serving as a confound. So it might be something like sex, it might be age, it might be diagnosis, it might be degree of experience playing video games. It could be whatever we think might act as a confound, as a problem. And so we can create pairs of participants that are equal on that variable, and then randomly assign one member of each of those pairs to the experimental condition and one to the control condition. So there's that. There's the random assignment part, but it's not purely random because we started off by making sure that we're assigning out of these pairs that are matched on the criterion. We end up with ideally groups that are fundamentally the same because we made sure that whatever this variable was that we're worried about got equally distributed between the two groups. Let me give you an example. Let's say that what we're concerned about is sex being a possible confound. So I got this nice group of people off the internet, don't know who they are. It happened to contain 7 females and 6 females. So obviously what we're going to have to do is get rid of the extra participant, just randomly decide which of these extra females can go. And then of the remaining 12 participants, we're going to match the pairs, match them into 6 pairs of female, 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 male, 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 right? And then we're going to randomly assign one member of each pair to the control condition and one member of each pair to the experimental condition, so that we have now distributed that characteristic of sex so that half of the males are in the experimental group, half the males are in the control, half the females are in the experimental group, half are in the control. This is a really good strategy if you have identified something that you think might be a confound, and you're like really worried that this might interfere with the effectiveness of your independent variable or might muddy the interpretation of your independent variable. Using a matched pair procedure allows us to sort of on purpose. It's not randomization anymore because we did match them before we randomized them, but we can on purpose make sure that we don't have an imbalance. You'll notice in a lot of psychological research there are imbalances in the number of males and females in the experimental and the control group because they don't do this. They use random procedures instead, and so there's already on average way more females in psychological research than there is males. But when there are males, they aren't necessarily evenly distributed between the groups, and so you end up with a possible problem, possible confound. So this is one way to get around that. The last example would be natural pairs. Sometimes people exist in natural pairs, and so we can use those pairs and then again randomly assign from the pairs to the conditions. And so these would be things like people who are biologically related. Let's say we have the pleasure of having groups of twins available to us. We might randomly assign one member of each twin pair to the experimental group and one member of each twin pair to the control group. And that way we ensure whatever it is that about these two twins has been equally distributed between the groups. They do the same kind of thing with like social relationships, like club members or something. Okay, so maybe we know that we have some people who belong to this club and some people who belong to that club. Well, let's pair them up and distribute them equally between the groups so that we can kind of get rid of that confound. So natural pairs and matched pairs are very similar. The exact procedure is exactly the same. It's just that in natural pairs, you didn't have to pair them up yourself. You can they already came to you like that. All right, good time to stop. We'll come back and talk about dependent variables next.